There is, but YouTube does its own develop thing, which is very expensive. I think that's going to be.
I feel like it wouldn't be either like have to set up service.
It would be, except I'm pretty sure no one in, I'm pretty sure no one. It's just knows how to use OBS except me.
Oh, it's not that hard to use it.
Yeah.
You press the buttons and it does the hard thing.
Let's go! Oh. Fire, absolutely fire.
Make sure you read the buttons.
Indeed, it is me too. We. Oh, I'm so glad. Alright, so I can confirm it does need all those details before the soups. But luckily it started. Yep, it's working.
Okay, cool.
I'm just gonna start watching the YouTube live here, okay?
Yep.
Should I turn off my camera?
Probably.
Turn on your mic and see if it loads up. And also you can share it once.
What am I sharing?
Oh, your mic works?
Yeah.
And also share your Google Slides or your stream into the Zoom so that it can come up on the screen.
Oh,
Quick check, make sure you don't have anything that want to be visible on your computer open. Probably before you do the live stream.
oh, true.
Because people have had issues with that in the past.
Uh-oh. Whatever. Can't really do anything about it now.
I can't say I'll be walking through these vlogs later, so don't worry about it. I can cut it out if there's anything you felt about it.
Okay, sure.
I mean, there's still like strings, right? So like, it's just a general safety thing. Always, before you plug your laptop into a display, make sure that you close every single thing. It's like private. It's like that's how you accidentally leak like important documents or whatever.
That's how you dox yourself live, yeah.
Dox yourself, like leave an exam or something. Plenty of things that can go wrong.
I leave me for exam.
I mean, you don't have that choice. I don't do that.
What? You have laptop?
Sorry, what are you saying?
Honor?
I'm gonna edit the slides now so I can edit the acknowledgement.
Okay. You just move the slide.
I mean, you're already screen sharing. So you might want to stop that.
Oh. Okay.
If you want to stop the screen share, then just give them the like. If I'm here and you say something incorrect, I'll tell you. It's the only thing I'm hanging up thinking.
Oh, this will be really short because I'm on my lunch break right now.
So the workshop's gonna be short?
Yeah.
Okay, that's fine.
I didn't know I was working today. These guys like updated my. These guys I work on Wednesday, Friday, and they just like assigned me the whole week this week. No one's that.
You tell them no.
These guys like predatory.
That you kind of say no.
Bro, you're an employee, you gotta use your union rights sometime, right?
I mean, like you can, if you say no enough, they'll start assigning shifts to other people. Like you can just say no. That is a right as the actual employee. You don't have to give notice.
Sure, rights
Other than like 1 hour of notice. But you know, I'm not sure you can finish this whole thing in half an hour. So
Well, oh no, my lunch is an hour. But also,
you've been here for like 30 minutes.
sorry if I'm.
Oof. Now I'm gonna feel bad when I leave.
You're probably gonna leave at the same point that I will leave. But I've given like practice problems. The practice problems and we drive them to the years practice problems. The weekends. Like, a bit rough, but
Said what fuck. Why coming?
Oh, wait, yep.
You're missing some sorting that room on there.
Yeah, I don't have time to make this slides.
But insertion sort, selection sort, heap sort.
Each sort is covered, but. I think, well, obviously like pointers as well.
Like pointers, comparison, I feel like the ordering is a bit off as well. It's like a reverse order to how it's called.
There's only selection for double.
Yeah, I think that. Subject for more recently. But. First.
Like see some up.
In general, see stuff like miscellaneous. I didn't really. Personally, like, some people ask me questions about what do I point out as. Why is it? Just like, that leads into a discussion.
I'm also seeing like abstract data types.
Oh, that's data structures, that's exciting.
You put this as keys, keys calculated with BSDs, you also need priority queues, stats.
Oh, it's in the data structures. It's just like, once you introduce them, first and say that on top. You can go and take see. Some page. But like. Yeah, you visualize it. Annoying.
I'm gonna put that.
So I don't really have a ton of fun, you just can't really do results.
Maybe just screenshot it. Okay. Oh, why is that not appearing? All right, so I think we're gonna make a start, even though there are only 3 people here. Welcome to the FOA exam revision workshop. And if you want to follow along with the slides, you can use this URL. Just type tinyurl.com/FOA revision slides to follow along on your own device. Today we'll be covering these 5 topics mainly. We're going to be starting off with data structures. It's chapter 1. First data structure we're going to cover is linked lists. So a linked list is composed of nodes which hold data and a pointer to the next node, and sometimes if it's a doubly linked list, a pointer to the previous node. And I guess searching for elements in a linked list is going to be O of n, where n is the number of nodes in the linked list. And compare that to an array where you have O of 1 indexing. Why do you think we would use a linked list at all in that case? Does anyone have any ideas? Ooh. That's not good. Screen share. Okay. Okay, sure. Does anyone have any ideas why you might use a linked list over an array?
Faster deletion and insertion.
Yeah, exactly. Faster deletion or insertion. And can you explain why a little bit? Why?
So for example, we are trying to add a new value to at the start of the array. So we'll have to shift everything by 1. So that will have a time compressible for n.
Mhm.
And if we are using a linked list, we can just link the node that is at the front of the current list to the new value,
Mhm.
which would give O.
Right. So to sort of visually explain what he was saying, let's say you start off your linked list with the node 2, then to insert, or I guess let's say you have a very large linked list already. These nodes are all linked to each other. And let's say you want to insert a new node, node 1. Now, when we create the node, all we have to do to insert it to the head of the linked list is just link it to the previous head. So this was the previous head. And now we make this new node the current head. And that happens all in O of 1. So O of 1 insertion to the head of the linked list, whereas in an array, we would have to shift over the elements. If we want to insert a 1 at the very start, then we would have to shift 5 over, then shift 4 over, shift 3 over, shift 2, and then insert your 1. It's not being streamed.
It's not sharing.
Okay.
Checking my hands again.
Does that work if I stream? Does that show up, Ref?
Good thing, I don't know that.
Wait, what do you mean, Raf?
Oh. But you,
Oh. Whoops, okay. Can you see?
Yep, now,
Can you see this?
yes. we can
Okay.
see that.
Yep, so pretty much, sorry, just like summarize what we were talking about with linked lists, the head, when we want to update the head or like update the first element in the list, all we have to do is create a new node, for example, 1 here, and link it to the previous head, which was 2, and then make 1 the current head. That gives us all 1 insertion to the front, whereas in a normal array, we would need, let's say our array was this, we would need to shift all of the elements forward to insert that 1. So that runs in O of n, whereas this runs in O of 1. So that's one advantage of using a linked list. And I guess building on that property, it makes linked lists a suitable candidate for 2 abstract data types. And we have these 2, stacks and queues. And so if we were trying to simulate a stack using a linked list, what that sort of looks like is, imagine we have our stack here, 2, 4, 3, 5. Huh?
like, slide across.
Oh, right. So imagine this is our stack, and this is how it was built. The analogy that you draw is like the linked list starts with a node 2, and you insert to the head again. So you create a node 3 and then link it to 2 because 2 was the previous head. Now you add like 4, create that new node and link it to the new head. And then 4 becomes the new head, and so on and so forth. When you want to delete, what you do is you take the head of 4 and you make the head the next element. And then you free like this node. You free the 4. And what that does is just pops from the stack. That's simulating popping. So that's sort of how we replicate a stack or implement a stack using a linked list. Now, the second abstract data type we can create is a queue. And let's draw out a linked list here. Now, does anyone have any ideas how we can implement a queue using a linked list? So let's assume that we have pointers to the head and the tail, right? Do we remember how a queue works as sort of abstract data type? Yep.
Like the first, like the thing at the front, the head, and then like you shift like the second one forward, and then after that you like delete the second one, which is now the head of the queue, and then like goes onwards until like there's only like one should I say person like the head of that queue.
Yeah, so what you're describing there is we're going to dequeue. We're going, oh,
Like,
yep.
like put the new, should I say person at the like the tail part, like when you're enqueuing?
That's the tail part. Yep. Yeah. So like, you're talking about the NQ, right? NQing of a new person. Yeah. So yeah, that was good. We put this new person or this new node at the tail whenever we want to NQ. And whenever we want to DQ, we use the head pointer. So to NQ, we use the tail pointer. To DQ, we use the head pointer. To like demonstrate what she said, we sort of erase this head to DQ and move the head over to the next node. And that sort of simulates a queue. Cool. So let's move on to our next data structure. Were there any other questions about linked lists and how they could represent stacks and queues? Oh, yeah. So just FOA revision slides. No problem.
I have a question. Why would you use a linked list for a stack instead of an array?
That's a good question, Casey. So you might ask why. Oh, well, she did ask, but okay. So there are two ways you can implement the abstract data type of a stack. Huh? Oops. Keep forgetting. Anyway, there are two ways you can implement this abstract data type. One way is what Casey suggested of using some array. Now, you do know that like an array is of fixed size in C, and I guess to resize it, you would have to allocate new memory, move over all of the elements, to this new allocated memory. And yeah, I guess that's how it would work. You would just need to resize as the array grows. For example, if our capacity for our array is, let's say, four elements, and we want to add a fifth element, well, we know that our array is fixed size. So we allocate some new memory over here, which let's say has a capacity of 10. Say 4, a capacity of 10, just arbitrarily. And now we copy over all of the elements to this new array. And then we can insert the 5 because there's enough space now. And that's sort of how we simulate adding elements to a stack. And to pop, all we need to do is just, keep a pointer to whatever's our last element. And you might ask, why would we use that? Why would we use that instead of a linked list or like vice versa? And we want to avoid this sort of copying over by using a linked list, because in a linked list case, you're not allocating contiguous blocks of memory and there's no need to resize because when you keep adding elements. I can't.
I have a couple of things. Instead of throwing you under the bus, I can just.
Yeah, okay, that's fine.
Wasn't planning on doing this, but here we go. Do you want to use that?
Yeah, sure.
Okay. So, couple notes. The key differentiator between whether to use an array or a linked list or a dynamic link structure sort of depends on the time complexity you need of a specific operation. Now, in the case of a stack, in a generic case, if we consider the insertion or pushing to the stack and popping from the stack, if you always keep track of an index of the top of the stack, so I put insert 5, how do you move something? Which button?
Select.
Okay, select. And then I want to insert another value, let's say 6. that took me O of 1 time. I just shifted across. Now, this idea about resizing does have a consideration, but I will note that this gives you amortized O of 1 insertion. What this means, the amortized means spread out per element. This is what's usually called in some languages like a vec type structure, but basically it's a dynamically sized array. And the idea is if you multiplicatively increase the capacity by, for example, multiplying by 2, let's say I started with a capacity of 4, in this case, then by doubling every time, this is exponential growth. And if I start with a capacity of 4, let's say that's O of 1 time to initialize, and I have like 7, 8. In order to double it, I have to copy, let's say, 4 things. So now I've done 4 copies, and I have 4 elements in my array. And if I double it again, which ideally is infrequent because I'm doubling exponential growth, I now have copied 4 things, and then the next time I copy, I'm copying 8 things, but always, relative to the length of the array, I've always copied less than n things. And because it's less than n, you can distribute out the copying operation to be O of 1 per element, assuming that the copying is not frequent because you're multiplicatively increasing, it's exponential growth. So that part is not particular consideration. And particularly in the case of a stack, because you're pushing and popping in an array is always O of 1, it's perfectly fine to use an array. And also perfectly fine to use a linked list. But sort of the array can be a bit simpler. If you contrast that to a queue though, and consider doing NQ and DQ, if I want to push or add an element to the end of an array, it's always O of 1. Let's say I want to put a 7 here, for example. But to NQ, I have to copy n elements over every time. So this operation would be O of n. So now, in order to do both NQ and DQ at the same time, I need to do one O of n operation and one O of 1 operation, regardless of which choice I make, which is arbitrary. Which is in contrast to the stack case, both push and pop is O of 1, so you don't really get an algorithmic benefit. In the case of a queue, if you use a linked list with suitable links defined, so if this is my queue now as a linked list, I have 1, 2, 3. Okay, not used to Brian's iPad here. Okay, and I have a tail and a head. Then if we consider the insertion at the head of the queue, it was, as Brian said, O of 1 insertion, you add 1 pointer link and then you update the head location. And to add something to the tail, this is also O of 1 because I have a tail pointer, assuming you have access to that. You add a link, you move the tail across. But to delete from the tail, what do we have to update? We have to update this node's next pointer. And if it's a singly linked list, you don't have access. So in order to get access to that red circled node, you have to start from the head, iterate through n-1 elements to get access to that node, which points to the current tail. So then deletion from the tail in a singly linked list takes O of n time. But deletion from the head, because you need access only to the existing head to move the pointer across, takes O of 1 time in a singly linked list. So if you want to be able to implement a queue in a linked list type, if it's singly linked, you should inherently then do deletion from the head and insertion at the tail. That gives you O of 1 and O of 1 time. If you did it the other way around, it's not symmetric in this case, and you do insertion at the tail, no, deletion at the tail and insertion at the head, now you have O of 1 and O of n. But if it is symmetrical and you have double links, for example, well, now it's O of 1, O of 1, you can make an arbitrary choice. So the considerations sort of depend on the circumstances and what operations you want to achieve. So the choice between an array and a linked list for a stack doesn't really matter, but for a queue, depending on your circumstances, it does matter a bit more. And for a stack, in the case of a linked list, you don't even need this tail pointer, because it doesn't really change anything to add. It's sort of arbitrary amount of one fixed size amount of memory, but you don't end up using it to get your O of 1 insertion and deletion from the head. So like if you wanted to save that extra tiny bit of space, you could also remove it. Sorry for interjecting randomly, but
Oh, that's okay.
that was what I want to say.
No problem. Did anyone have any other questions regarding linked lists and implementing them as queues and stacks? Okay, let's move on to heaps now. So a heap or a binary heap is a complete binary tree which preserves like a specific property where each parent, we'll talk about like a min heap in this case. Each parent is going to have a greater value than its children. Now, you see that in this tree here, where the 2 has, a lesser value than its children. You see that here with 2, where 4 and 5 are going to be greater than the parent. And you see that recursively applied to that property. See, 5 is less than 6 and 8, 4 is less than 9 and 7. And one cool thing you can do because a heap is complete. Complete means that every layer is going to be filled in the heap, aside from the last layer, which doesn't necessarily have to be filled with leaves. But if it has like some leaves in the tree, then these leaves will go from left to right. For example, in this case, we'll create sort of the same heap, just using 4, 5. So this, what do we think? Is this a heap or not? Does it satisfy completeness and like the heap property for all of its subtrees? What do we think? So all of the layers are filled out, except this last one. But we talked about how the last layer can be partially filled as long as the leaf nodes go from like left to right in the tree. So this tree that I've drawn actually does satisfy completeness.
Strictly speaking, it doesn't have to be complete, it's an implementation detail. So based on how you implement the operations to deal with the heap, it stays complete, which is important for storing it into a dynamic array. But you can also quickly have a heap using a link structure, which is not complete, and it's still technically a heap. So the property is specifically that recursively for every node is larger than its children.
Okay. So it doesn't have to satisfy completeness unless you want to implement it under the hood as an array, so like a flattened heap, and we'll talk about that soon. But the second property that this tree satisfies is that every parent has children with greater values than it, and so it satisfies the heap property. Cool, so this must be a heap. Now, what I was talking about with being able to flatten the heap into an array is using the complete shape. And what we can do is have this nice formula where the child of a specific node can be calculated by child, or like left child. So this is how you would index the left and right child of a node in a complete heap. So for example, let's see in this case, we're going to assume that it's one indexed. For example, let's take the children of 5. Oh, the children of 5. So in this index, 3, we want to find the children of 5 in this array. And we use the formula, so child 1, or the left child, is going to be 2 times I. So 3 times 2 is 6. And what do we see at index 6? 6. And we see that reflected in the diagram as well. Next, we'll look at the right child, which we do using 3 times 2, which is 6 plus 1, so it's 7. And we notice that we land at index 7, which contains an 8, and in the binary search, in the heap, we have that same 8 as a child of 5. So that is a way you can sort of flatten your heap into an array and represent it in a simpler form. There are a few operations that can be done on heaps and which makes them a useful data structure. First thing is insertion. And
Build heap should be at one.
it's you use bottom-up construction. So such a So the first operation is insertion, where we're going to be sort of demonstrate how insertion works. Use this, just draw this out 1 second. 9. Cool. So let's assume that we have the heap from the previous slide and we want to insert a 1. Now, since we attached like the children going left to right, we attach it to this 9. Say we want to insert this 1. And what we do is sift up from this 1. So we compare it to like its parent, and we see that 9 is greater than the 1, so we'll swap the nodes. Maybe I shouldn't do this in blue. So this now becomes the 9 that we were using before. And then we apply the same process to 1 and its new parent. Remember that we're trying to insert 1, so insert 1. And we apply the same process comparing these 2 nodes. So we swap them again because 1 is less than 4, and we want to maintain the heap property. And then when we compare one last time with 1 and its parent, we realize that 1 is still less than its parent, so we swap them again. And your final tree looks like this, where 1 is at the very top, and you'll notice that all of the nodes below all satisfy the heap popping. So like 2 is less than 4 and 7, and that applies to every single sort of subtree. So that's insertion. And because we sift up will run for log n operations. Does anyone know why? Well, we take a node from the bottom and it just like goes along and swaps, right, to the very top. Can anyone see why this is log n? So because of the tree structure, because the tree height, because you increase like nodes in each layer exponentially, so 2 to the 0 in this layer, 2 to the 1, 2 to the 2, 2 to the because it just continues. That means that the height of the tree is going to be log n. And so if you're traversing the height of the tree in sift up, that means your total operations will be log n as well. It will take log n time operation for insertion. So the next operation is like delete the minimum, and we can just reuse the same sort of logic. I think instead of going through it, because we have a lot of slides to get through, I'll just say that it is log n, and you can feel free to draw it out yourself on this graph. Some other operation, which is building a heap, is surprisingly O of n when you use a specific type of construction. I'm not sure if, I'm guessing not, they didn't learn. What
The
about-
one in analysis print is that, so it's fine.
Okay. But yeah, keep in mind that you can build heap in O of n time instead of n log n, which you might have seen from like your textbook where you just repeatedly insert.
The textbook one is also home, and I just
I
I'm
see.
just thinking because I forgot that it's dependent.
I see.
That-
Yeah, just an O of n operation. Heap sort, it's pretty much just you take the minimum element each time and then delete it, but then you store it in some array sequentially, and that's why it's n log n, because each deletion happens in log n time, and you do that n times throughout the heap. So we can think of heaps as implementing this new sort of abstract data type called a priority queue. And in a priority queue, we want these operations like inserting a specific item with a priority, and then checking which element in the priority queue has the highest priority, then sort of like popping that element, dequeuing that element, the most important one, or the most prioritized element. And how that maps to our heap is we just take this to be like, let's just say the minimum element here is the node with the highest priority. And that's sort of what we sort our heap by. Our most prioritized element is at the top, and that allows us to like see what it is in O of 1 time, and just insert in log n, but also delete and like dequeue our most prioritized element in log n as well. So moving on to hash tables. A hash table is pretty much just an array under the hood, which each element in the array is, you can think of as a bucket. Now, you might think like, okay, if I have some hash function, that takes a key, let's say we're trying to store like pets in our hash table or something, and we have dog, snake, and our array is something like this. We have some hash function that maps our string to an integer, which we then use as an index. This would contain dog. And you might ask, what happens when our hash returns the same number for two different keys? So for example, the hash for dog and cat they both return index 1. Well, then you need a way to sort of resolve this collision. And there are two methods to do that. One is separate chaining, which involves each bucket being a linked list. As you can see here, the bucket is a linked list, and when you try to query, let's say cat, you have to iterate over the entire linked list to find your cat entry. The other option is open addressing. So instead of placing cat in the same bucket as dog, you sort of walk the array to the next available index that's free, place cat there. And now when you want to query cat, it'll get you to this index of 1, but you'll have to walk because you realize that it's still dog. You'll have to walk to index 2 to get cat, and that's how you find your key. So those are the two methods of collision resolution in hash tables. And when we don't consider collisions at all, we have this average cost of OLV1 for insertion and OLV1 for lookups of a key. However, when we do have collisions, there's like a worst case where you iterate over your entire collection of like pets, let's say, and that can sort of degrade to OLVN, where n is the number of pets in this example. Were there any questions about hash tables before I move forward?
Addressing can be seen as shift into the next available balls.
Yes. So if a slot isn't free, for example, like imagine we're inserting 10 here.
Yeah.
Let's say that it hashed to bucket 2, but cat is already here. So what we do is look at the next available bucket. And if this is free, then we just insert 10 in bucket 3.
How about if we out of capacity?
Yeah, if we're out of capacity, we sort of keep track, we keep a record of how many elements we have stored already in our array. And if inserting another one is like, we're already out of capacity, then we need to move all of our elements to another bucket, to another hash table. So we'll create another hash table with a greater size. That's normally how we address lack of capacity when inserting. Okay, so moving on to binary search trees. Now, a binary search tree maintains the property that each node is going to be, I guess each parent node, the children on the left of that parent node are, oh, okay, so I should clarify. Let me draw this out. So, in a binary search tree, this is like some root, and or this is any node in the graph in the binary search tree. And this node's value, let's call it V. For the left subtree, all the values in the left subtree are going to be less than V. Less than, or like it depends on your condition really, they could be equal to as well. They're all less than or equal to V. And like symmetrically, all values in T2 are greater than or equal to V. That's pretty much the BST property that's applied recursively to every single node in the BST. And so we'll look at that explicitly. So you see that 8 up here, all of the nodes in the left subtree are less than 8. All of the nodes that are in the right subtree are greater than 8. You see that with 3 as well. All of the nodes that are to the right of 3 are like greater than 3. All of them to the left are less than 3. So how do we look up a key in a binary search tree? Well, it's similar to how you would look up some value in an array and just call binary search normally, where you look at the start node. Let's say we're looking for 6. We say, is 6 less than or greater than 8? And we know that it's less than, so we move to the left subtree. It must be in this left subtree, right? We look at 3 and say, is that less than or greater than 6? And we know that it's less than, so we move to the right subtree of 6 of 3. And there we find 6 as one of the leaf nodes. And so that's how we look up a key, and that takes of log n in the average case, because all we're doing is just traversing down the tree, and the height of the tree, as we learned before, is log n. Now, it does have a worst case of n though. Can anyone tell me why? It might be O of n in the worst case, to look up a key.
He doesn't fix this. So we'll just keep on.
So if the key doesn't exist, let's say 7, right? We might look at this and say, okay, it's in the left subtree. We look at 3, compare it to 7, and say, okay, it must be greater than 3. And we end up at 6, and it must be greater than 6. There's no nodes, right? However, the total number of operations that we've done is log n still, right? So that is still, even though the key doesn't exist, our search was still effectively O of log n and not O of n. So can we think of any other reason why it might be O of n? So let's say we have some tree like this. Do you guys still think this is a binary search tree? Why or why not? So this is still a binary search tree because notice that in that 3 over there, all of the nodes in the left subtree, which is non-existent, are less than 3. So it satisfies that property. All of the nodes in the right subtree are greater than 3. So that means that 3 is a valid binary search tree. And similarly for all of these nodes below, it's applied recursively. So this, in fact, is a valid binary search tree. But now, think about like the worst case in searching for a 9 here, for example. To search for a 9, you'd have to visit all of these nodes, right? And it sort of looks like a linked list search when you think about it, right? And so to search for a 9, that query is O of n, because we've explored all n nodes in our tree. Similarly, imagine if our tree was like this. Do you guys think this is still a binary search tree?
Yeah.
Yeah? Because like if we take this 5 here, all the nodes in the right subtree are greater than 5, right? And so on and so forth, like all of the nodes in the left subtree of the 10 are less than 10. So this is still a binary search tree, and the search goes the same. Let's say we're looking for the 9. We have to traverse the entire tree to get to that 9. And so that search is of n. That's why the worst case complexity of a search on a binary search tree is of n. To insert a key, it's exactly, well, it's very similar to looking up a key. So like all you do is like search for it, and if it's not there, if it doesn't exist, then you just add it there. For example, I guess with this 9, let's say we're searching for 11. We would simply just add it to that 9 once we've searched for 11. And yeah, like similarly to the search, it has a worst case of n for the same reasons. Were there any other questions regarding binary search trees?
The deletion isn't scope because it was only assigned.
Okay. Yeah, so I don't have slides for deletion, but yeah, I mean, I think I'm sort of like running out of time. So I might just keep. Yep. So there are 2 ways to implement dictionaries now that we've talked about both hash tables and binary search trees. We realize there are 2 ways to implement dictionaries. But what are dictionaries? We need some way to like insert and search and delete in both of them. Right? And that sort of satisfies what we can do with both a hash table and a binary search tree. However, like if you think about it, to perform an insertion or a search or a delete on a binary search tree, it seems like overall worse compared to a hash table. So I guess the question I have is, if a hash table is faster on average, like why would you ever pick it instead of a binary search? I mean, why would you ever pick a binary search tree instead of a hash table if, you know, the insert, the lookup, deletion in hash tables is faster overall?
It will communicate to calls.
Yeah, so I'm thinking of like, if you wanted to add an extra feature, your binary search tree would be more beneficial to use than your hash table in a specific case. And this specific case that I'm referring to is if you want to take like the maximum or the minimum in your binary search tree, because you'll notice that the leftmost subtree is the minimum node in a binary search tree, and the rightmost subtree is the maximum node in a binary search tree. For example, like here, 3 is the minimum node, 11 is the maximum node. So you can sort of extract the minimum or the maximum in your dictionary in log n time when you use a binary search tree instead of a hash table. So that's like sort of trade-off. Oh. Okay. Chapter 2. It's been like an hour. Okay. So like we'll move on to string searching, which is pretty much like just control F, right? How do you find a pattern in a larger text? And there are 3 ways to do this using brute force, KMP, and suffix arrays.
Nothing.
It's not examinable? Okay. Let's skip that then. The brute force approach is very much just, oh, is it still streaming? I think I stopped screen sharing. Okay, I stopped screen sharing. Okay. So the brute force approach, let's say this was like your pattern and you wanted to find it in this string. You just look at each of the individual elements one by one until you find like a mismatch, which is actually at the very start here. Then you shift over your pattern. There's a mismatch, so you shift over again. And yeah, you keep on doing that. And intuitively, that's of m times n, right? Where m is like the length of the pattern, and n is the length of the overall text you're searching through.
Correction. Suffix is my bad. Wrong one. BMH is not.
Yeah, okay. Okay, so suffix is accessible.
Go to the lecture slide. Anything that unofficial.
Yeah, refer to the lecture slides. Now, I guess let's go back. Yep, so of n times n time to perform a brute force string search and constant space, because all we're storing is just indices. So KMP sort of builds on brute force search to find a pattern. We'll go to this example again. Now, let's assume that you're a brute force search and you've stumbled across like this case here, or this iteration, and you look through each of the letters, A, B, A, B, and your mismatch is at the very end here, or one of the very ends, A and C. Now that's like pretty unfortunate, right? You nearly matched the whole pattern. What brute force says or proposes is, okay, let's just try with the next, let's shift it 1 to the right and try again, like all of that, and waste that sort of computation that you did. What KMP suggests is, let's just ignore these for now, right? Our first mismatch was here, and let's pretend that it doesn't exist. And if we were a brute force search, we would go like shift to this way and say, does this match? Does this line up? And if it doesn't line up, then like nice, but it doesn't. This doesn't line up either, according to our brute force search. We'll like go through all of them. This won't line up either. However, this does line up. This is the first one that does line up. And what if I told you there was a way to skip all of that computation where we didn't have to shift each one individually and try each one individually? All we need is a few observations. The first one is realizing that up to that first collision, these two substrings are the same. They're the same. And what we're effectively doing is when we shift to here, we want to see if this prefix matches the suffix up to that first collision. And because they're the same string, what we're effectively looking for is the longest prefix that's also a suffix of entirely the same pattern. And we know that here, in this pattern, the longest prefix suffix is AAB, which is of length 3. And you'd have that recorded in your failure function. Failure function is pretty much just like the longest prefix suffix, right? Or the length of it. And here it's of length 3. Notice like AAB,
A. And
what you realize is when you go here, you're trying to match a prefix of length 6 and a suffix of length 6. Prefix of length 6, suffix of length 6. And since your longest prefix suffix is 3, you already know this is going to work. So you don't have to compute anything. You just realize, okay, this is going to work because, you know, I'm matching a prefix of length 6 and a suffix of length 6. So you just keep going. You don't have to do any iteration. You say, okay, it doesn't work on 6, doesn't work on 5, doesn't work on 4, but it does work on 3 because we've already computed that the longest prefix suffix is 3. Then you just start comparing the next letters from this element because you know that the longest prefix matches with the longest suffix, and you know it's actually like a substring that matches. And so that's like how KMP saves computation intuitively. If you wanted to play around with something yourself, you can use this algorithm visualizer, which Casey whipped up, which can show you like the pseudocode of KMP in your own time and show you how it sort of matches the string. So the link to this is, I mean, if you wanted to write it down now,
On Ed.
yeah, it's on Ed. I don't know that, but yeah, that's pretty much how KMP works intuitively. Now, suffix arrays are another way to search these for the substring or for a pattern inside a large text. And what you're doing is just taking your large text, for example, banana here, and creating a new array with all of the suffixes of banana inside. Except instead of storing the entire string, you're just storing indices, so it's sort of lightweight. And then notice that for your pattern, you can just binary search on this new array that you've created. And if you get a value, if you get a substring that's equal, for example, let's say we were querying B, A, and A, like Bana, then maybe we look at what this is like. Just for example, this wouldn't happen in the actual binary search, but comparing it to Nana, Nana would be less than Nana. So we know it's like over here somewhere. And you sort of realize that banana is part of the banana substring here, and we just return like that and say, hey, it's a pattern, it's a valid pattern substring inside the text.
That's also on the visualizer.
Yes, so you can also use the visualizer to for suffix array search. Oh, okay. But yeah, have a play around this like really cool tool. I do have to like go soon. Did you want to take over?
And I have like
Set up Zoom?
close a lot of it.
Oh, okay. Okay, since I do have to go, this is sort of like a skim of all the rest of the slides. So there's like a quick sort and merge sort and their comparisons. Then we covered like complexity analysis here, just very briefly. I think don't even worry about this slide. Just like delete this. And then function, there's some slides about like function pointers and what void star does as a pointer and how it enables generic programming. But I I'm really sorry. I do have to go. I've got like work. But yeah, I didn't cover in these slides specifically these topics. So you might want to revise those as well. But yeah, there are some like practice problems, which I'll leave up for a second, which you can try for the remainder of this session. This is like AC's algorithm visualizer, but all the rest of these, tinyurl.com/FOA practice and FOA leak codes. These are sort of resources that I've chosen for you guys to like practice for the exam. However, if you haven't done ed exercises, I highly suggest you prioritize those, completing your EdStem exercises over doing these. This is just like any additional support you might need in preparation for the exam. But yeah, like, thank you guys for coming. That's the end of this presentation. I really do have to head off to work. But yeah, thank you guys for coming.
You got one first.
What is it you?
No, okay. Probably hear me, I'm guessing. Okay, so unscheduled extra stuff because I wasn't planning on being here. If you don't know me, I'm Casey. I'm also one of the tutors. Anything I say right now is also unofficial advice, despite being one of the teaching staff, because this is not endorsed. I'm not currently being paid to be here, so please take that in mind. Okay, so you've seen a decent amount of things. I guess on the list left is sorting. So in terms of sorting algorithms you've seen, there's a relatively short-ish list, but it's kind of long in some ways. So we have insertion sort. I might just list them out to start with. Selection sort. We have quick sort. We have merge sort, heap sort. Did I miss any? I feel like that's all of them. Fact check me, please. Okay, well, I may be missing one, but in any case, we'll start from here. So the way I like to do this is always think about what is the shortest description I can give for the algorithm. And in the case of insertion sort and selection sort, it's pretty straightforward. You can fit it in one sentence. For insertion sort, it's take the first element of the unsorted section and insert it into the sorted section. So I'm not going to write that whole sentence out, but as an example, I have 5, 1, 2, 3, 8. I start with my sorted section being one element. Implicitly, you could start less, but it's not, there's no point. And I have an unsorted section. So the key benefit for us is that because the sorted section is sorted, all we have to do is insert backwards until we're larger than the preceding element. So here, I want to insert 1 into the sorted section. I see that 1 is smaller than 5, so I'm going to swap it backwards. So I swap back with the 5. I've done 1 swap, and now I have 5 and 1. So I'm sorted because 1 is larger than nothing. So then my sorted section has now been increased by 1, and I've inserted 1 thing. So now I continue on, and I have this 2 element, and I want to insert 2 into the sorted section. I see that 2 is is smaller than 5, so I have to swap it with 5. So I've done 1 swap, and then I now see, okay, 2 is larger than 1. We've now got a sorted array again, so the sorted section is now 1 larger. Again, because 2 is larger than 1, that guarantees it's sorted because it started sorted. And you just continue doing that same thing. Now we're going to insert the first element of the unsorted section into the sorted section. We swap it with 5, and then now 3 is larger than 2, so we're all good. And then with the last one, 8 is larger than 5, we're done. And in our best case scenario, it's already sorted. We only do 1 check every time. We've done O(n) things. In the worst case, if it's reverse order, I have to go backwards 1 time. So I go 5, 4, 3, 2, 1. I start with it like this. I see that 4 is larger than smaller than 5. I do 1 swap. Then I have 4, 5, 3, 2, 1, and my sorted section is now here. And I'm now going to do 2 swaps, and then 3 swaps, and then 4 swaps, and then n-1 swaps at the end. So that sequence is one you'll see a lot in the subject, or have seen a lot in the subject, of like 1 plus 2 plus blah, 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 plus n-ish, gives us, in this specific case, if it's just n times n plus 1 over 2, proof. I always like to mention, because it's relatively straightforward, if you put things like so, and you count them, there is n elements, and each element sums up to n plus 1. So then you've added 2 of them, you divide by 2. But proof not important. There's the result. In this case, we had n-1, so then this becomes n-1 times n over 2. And that thing is very useful. It comes up in lots of cases. So a thing to remember for this and other subjects. So worst case, insertion sort also over n squared, if we're considering nodes visited. And again, the one-sentence description is, take the first element of the unsorted section and insert it into the sorted section.
And then from that, you can sort of reason about implementation with loops and such. For selection sort, it's similar, also has a one sentence description. It's select the next element to be sorted from the unsorted section. So if I start off with 1, 5, 1, 3, 8, 7, this entire thing is my unsorted section. And my goal is to find the element that should be at the end of the sorted section, which is right now has nothing in it. So I want to find the element that goes where the red arrow is pointing. So now I have to search the entire unsorted section. I don't have any nice sorted property to check for things. And after checking all n elements, I determine that 1 is the next element to be sorted. So I swap the 1 into the sorted section with the 5. And now my sorted section contains 1 element. And my unsorted section now contains n minus 1 elements, or in this case 4. And again, I check n minus 1 things. I find 3. I put 3 at the end of the sorted section, continuing on. Now, always, regardless of if it's sorted or not, I have to scan through the whole thing. So always, I'm going to be doing n checks, and then n minus 1 iterations, and n minus 2 iterations, and so on, until I get to the last element, which I'm doing 1 iteration effectively. And that same sequence again gives us n times n plus 1 over 2, so it's big O of n squared. So no best case of O of n like insertion sort. I will note that selection does only do n swaps, whereas insertion sort does do n squared swaps in the worst case. So there is a bit of caveat there. If maybe your swaps are more expensive than iterations, something to consider. But again, the one sentence description for a selection sort is select the next element to be sorted from the unsorted section and put it at the end of the sorted section. Where it gets annoying is quicksort, so we're going to leave that for the end. Next one is merge sort. So with merge sort, the idea is we want to split up our array into an easy to sort case. And our easy to sort case is if an array has 1 element, that is already sorted. So that's the goal. It's a divide and conquer algorithm. So we divide up our array until we reach this very simple case of 1 element array. So let's say I start with 5, 8, 3, 6, 1, 2, 4. My goal is keep dividing until I have 1 element arrays. So in this case, I'm going to divide it into 2 halves. I have a 5, 8, 3, 6 half, and a 1, 2, 4 half. I'm going to do this recursively. So I split these up again. I'll pick a new color. I have the 5, 8 half and the 3, 6 half. And then I have the 1, 2 half and the 4 half. Do it again. 5 and 8, 3 and 6, 1 and 2 and 4. And I'm going to put boxes, maybe just to make it more clear, that each of these are arrays. So now that it's been split up into our lovely single element case, it becomes a lot easier to reason about how to sort things. So these are all just individual arrays. So in order to merge, which is the next step, I'm always going to consider from the first element or the current element in each array, which one is smaller, and I'm going to put that into a new array. So from 5 and 8, which one is smaller? 5. So I put 5 as the first element of the new array I make. So I have 5, and then this is now empty, and I put the 8 in because that's the only remaining one. So the 8 goes here. And I do the same thing for the 3 and 6. So this one is also sorted. 3 is smaller, 3, 6. With 1 and 2. Also, the 1 is smaller than 2, so the 1 goes first and then the 2. And the last case, well, we still have a 4 on its own, so we're not going to do it yet. And then we do the same thing again, merging. So I will now want to merge into an array of length 4. And again, I have to keep track of the starting element of each of these. So I'm asking, is 3 or 5 smaller? 3. And then, importantly, I move the little arrow across because there's more elements to be considered. So now I'm asking, is 5 or 6 smaller? 5 goes in, and then I move the little arrow across. Is 6 or 8 smaller? So I put the 6 in. Oh, I was using green. I'll continue to use green. And then there is no more left in this one. So inherently, I just continue out through the rest of this array. So I put the 8 down as well. And then I do the same thing over here. I want to make an array of length 3, and I'm considering this one. Oh, that's not the right shape. This one, and I put the 1, then the 2, then the 4, applying the same logic. And then again, one more time, one last merge operation. We have the smaller of 1 and 3, which is 1, and then we put the smaller of 2 and 3, which is 2, and then the smaller of 3 and 4, which is 3, and then 4, and then 5, 6, 8. And we've done our merge sort. 2, 4, 2 4s. Oh, so if it's 4 here, you mean, and then 4 there? Well, it doesn't matter which one you pick. It's arbitrary. If your code picks the left one or the right one, it will give you the same output.
But is it like 1, 2, 4, 4, 5, 6, 8, or just 1, 2, 4, 5, 6, 8?
Oh, because we have an array and we're sorting, we have to keep both of them. So it's going to just move that little arrow past. So it would put, in that case, if this is I'm not going to change the previous elements, but inherently it would just be 4, 4. Now, notably, if there's other data attached to this, not just a number, the ordering might matter. So generally, the choice to make is we want to go for a stable sorting algorithm, which means we keep the ordering of equivalent elements. So in our original array, we look up, there would have been a 4 here, and this 4 is preceding this 4. So if we always take the leftmost one, we keep a stable sorting order, which means that things will be in the right order. So the canonical choice here is that this 4 gets chosen first. So that 4 becomes this 4. And then we move this little arrow forward, and then we use this 4. And because stable sorting order is useful, especially if you're doing stuff which has other data attached. Not every algorithm is a stable sorting algorithm, but this is one of them. Does that answer your question? Okay, cool. So inherently, the idea behind merge sort, divide and conquer algorithm, you split in halves until you get to the easy case of already sorted 1 element arrays. Then you want to merge them together. And our analysis for the time complexity, sort of, if we look at this, if we split it in half nicely every time, in this section here, we're going to have log of n levels because we're splitting in halves. And in each level, we're doing n operations to do n merges. So that gives us our n log n. That's the splitting part. The merging part happens sort of on this layer, but sort of you can sort of combine them together. So we end up getting n log n time for merge sort. And this is a worst case, but we do require some extra space in order to be able to do this recursion or other equivalent method of implementation. So there is a bit of a trade-off there, use a bit of extra space, but you do get n log n time complexity. Have I lost anyone? So in order to do our merges, for example, if I'm merging the 5 and 8, that requires me to iterate through 2 elements. And then to merge the 3 and 6, that's iterating through 2 elements. And to merge the 1 and 2, that iterates through 2 elements. So then in one layer of merges, I've done n steps. And then in the next layer of merges, I have to iterate again through n steps. And then the next layer, I'm iterating again through n elements. And I'm doing that proportional to log of n times, because each of those layers comes from splitting up into halves, which gives us sort of the same property of trees we normally have, of if you halve every time, you're going to get log of n layers in our tree. Does that make sense? Okay. So that was our merge sort 1. So that's another one off the list of the relatively straightforward ones. We have heap sort, which comes from before, that Brian mentioned. As a recap, if we have a heap, it is easy to always find the max or min value. If it's like a min heap, the min value takes O of 1 time, or the max value takes O of 1 time. And then to remove a value from our heap, it always takes log of n time. So if we repeatedly call the removal function, after removing the maximum value which we found, that's going to take a log of n times, because we're removing n elements. So we end up getting our log of n log n time complexity. Now, a notable thing is building the heap is O of n time, but doing heap sort takes n log n time even though you're doing what seems to be a similar operation. And the exact details of the derivation are in the lecture notes if you want to look. But sort of building the heap operation, if I, where is it? Draw a picture, and I have, let's say, a min heap, and I put some things in there. So we're going to have a 5 and a 8, 6, 7. This building the heap operation considers from the first non-leaf node, so the 3, then backwards if we do it in order. And every single time to build the heap, we're doing a sift down operation, which will take log of n time. But because we're doing it in this specific order, we're only doing exponentially less sift downs every single time. So when you do the maths out, it's in the lecture notes. That ends up taking O of n time. It ends up doing 2n iterations if you look at the derivation. But doing heap sort doesn't have this benefit because we're always sifting down from the root. And because we're always sifting down from the root, that means we're doing the expensive part in such a way that that overpowers the expression. And so we end up having n log n time for the heap sort part. Because to do heap sort, it requires removing the root element and then sifting down. And to do a removal, for reference, I am skimming a little bit, so please tell me if I need to come back, but I am cognizant of time. We would swap with the last element. So for example, I swap the 1 and the 7. If we have this in an array, this will take O of 1 time. So I put the 7 here, I put the 1 here. And then to maintain our lovely heap property, what we have to do is, well, first off, this is the end of the array. We can just remove it, it's in place. And then we have to call sift down on the 7. So if I sift down the 7, the sift down operation is going to do at worst log of n steps, because it's always asking, do I have a child node in this case, which is smaller than me? And if so, I'm going to swap with the smallest one if I have a min heap. So here, 2 is the smallest child, which is smaller than 7. So I'm going to swap the 2 and the 7 together. So the 2 goes here, the 7 goes here. And then now I'm going to ask, is there a child which is smaller? Yes, there's a 5 here, because I'm sifting down from this node. So I'm going to put the 7 in this location and the 5 here. And now sifting down on the 7 node, there's nothing left. And if you do that repeatedly, if you notice removing the min heap element, we have a 1, and then the next element to remove is going to be a 2. And if this is an array, essentially, slowly, we're going to be going backwards. Removing the elements is going to leave the next smallest at the end, which ends up giving us a sorted array. So because this log of n operation, if you do the maths out, still stays log of n, we have n log n time, and we don't require extra space, unlike merge sort. So heap sort seems like a great algorithm, and it is. But we have another one there, which is called quick sort, which is still often used in practice. And sort of the best algorithm is not always necessarily the one with the best time complexity. Sometimes, for given specific types of data, the benefits of one algorithm might outweigh another if you're doing a specific operation. And so that was our heap sort. We also have the last one, which is quick sort. And this one is, relatively speaking, the most evil of the sorting algorithms we're talking about, because it requires all these steps. So let's break it down sort of at the high level, and then I'll leave the specific implementation details sort of to having a look through the code and such, and ask an ed question here. So with quick sort, the overall goal is, again, we want to split it up into smaller, easy to do pieces. And our specific operation we want to do is first what's called picking a pivot value. So to write the steps out, choose a pivot. And then we want to partition around the pivot. And I'll explain what that means in a second. And then recursively do this on left and right. So there's a bunch of different ways you can choose a pivot. The key note about choosing a pivot is ideally to get a nice average case, we should be randomly picking the pivot value. More on that in a moment. So to start with an array like 5, 8, 1, 2, 3, 6, 4. If this is my array, I need to pick a pivot value. Now, for this specific case, a good pivot choice would be something always around the middle. So around the middle of this sequence of numbers would be around, let's say, 5. So that's a good pivot choice. A bad pivot choice would be number 1. And the reason this is a bad pivot choice is every other number is going to be to the right and none on the left. We want to balance the left and right numbers. So if this was the pivot choice, a valid partitioning would be 2, 3, 6, 4, 5, 8. The ordering here, I will note, is going to be very specific based on the algorithm. So pretend that is just some arbitrary sequence. We don't know anything about that. It's just arbitrary. And we have on the left here, nothing. If we have a good pivot choice, so I pivot around the number 5, now my partitioning step has to put a bunch of things on the left. So I have to have 1, 2, 3, 4, 5 is the pivot, and then let's say 8 and 6. And again, the ordering here is arbitrary. You cannot assume it's sorted or anything of those lines. And now, in this case, it's approximately balanced. Technically, the optimal choice in this case is a 4. If we have random data with random pivot choices, there is some mathematical proof you can do, which shows that the best, on average, it will be splitting in half. And if you want the extra math details, you can look up details related to the central limit theorem if you do further maths stuff. But basically, with large enough random data, there is more values around the average point. So it will split in half nicely on average, giving us our good average case. More on that in a moment. But basically, we've got to do this pivot, and we have to do this partitioning step. Now, this partitioning step is one of the hard pieces of KMP. How do you do that? And there is pseudocode and such in lecture notes, or you can watch lectures. But sort of the general idea behind partitioning is we can be done in a way that gives us O of n time to do the partitioning step. And again, it's because the order is not guaranteed on the left and on the right of the pivot. But what ends up happening is you can do one scan through the array, and you keep track of the equal to partition if you're doing 3-way quicksort, and the greater than partition. And with your one scan, you're going to be swapping things around either by moving FE forward or FG backwards until such point that they intersect. And because you're either always moving FE forwards or FG backwards, you end up with O of n time. Again, skimming details, refer back to lecture notes, or let me know afterwards. But that's partitioning. So once you've partitioned the array appropriately, running that O of n operation, and I have, let's say, 5, and then 1, 2, 3, 4, 8, 6. I then want to recursively call quicksort on each of these pieces. So if you do this with good splitting, you basically get what looks like the merge sort case from before. We split in halves, and splitting in halves evenly will give us log of n levels. And each of those log of n levels, we have to partition n elements. So, or rather maybe n minus 1 or n minus the number of equal to values. And because we're doing effectively what looks like a merge sort case, n O of n operation on log of n levels, the average case would be n log n. If you have bad splits, so you end up always partitioning based on the minimum value. So let's say I partition around the 1 instead, and 1 is now going to be sorted. I have my 5, 8, 2, 3, 6, 4. I'm then going to do this, and I pick a bad pivot choice again of the 2. I'm then doing n levels because I'm only taking 1 off every time. And every single time, I'm doing an O of n operation on n minus 1, n minus 2 elements, and so on. So my worst case for quicksort is O of n squared, which comes from the fact that I'm not halving it nicely. So that specific analysis sort of applies to how we think about binary search trees and how we think about merge sort and about quicksort. So if you can apply that same principle, and again, our lovely formula, 1 plus 2 plus blah, 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 plus n is n times n plus 1 over 2, you sort of get where the n squared comes from and where the n log n comes from. In practice, quicksort is commonly used quite often because it doesn't, it tends to be pretty good, even though it's not in the worst case that amazing. But sort of it depends what your specific use case is. And so if you can guarantee random data, the average case holds pretty well, assuming your pivot choices are random. But exact specifics, lecture notes. Yeah, so steps, quick sort in sort of one sentence. Choose the pivot, partition around the pivot in O of n time. Recursively do this on the left and right half. You can also have two-way quick sorts where you don't keep track of an equal to partition, which changes the complexity a little bit. There is some notes about that in the lecture notes / tutorial slides if you want to do some review. Sorting. What else to talk about? There was a bit about COMP before. I guess a bit of review on like syntax for things such as pointers. So, and I guess different memory sections. So we have what's called the stack section of memory and the heap section of memory. And these names are extremely unfortunate because stack and heap are also the name of abstract data types. But they mean different things. And in the case of the stack section of memory, it also implements a stack, which is a bit annoying, but the heap section doesn't. So in our program, when we run the code, we have our memory being partitioned into two different sections. We have the stack section, we have a heap section, and then we have some other sections which sort of vary, maybe like a data section or a read-only section where certain things will live, but I'll sort of ignore that part. The stack section of memory is where all our function variables are stored, and those have to be a fixed size. So you can't have a dynamically sized blah, blah, blah living in the stack because the compiler has to know this at compile time, and it will allocate the right amount of space in the program so that it will make it a correct size. So let's say you have a program that starts. We have our main function, which has some stuff inside of it. So this is a function that gets called, and notably, there is some machinery in the background which does some function calls and then calls main. But sort of, we can ignore that part and just say, okay, we have the main function. It has what's called a stack frame. Basically, just a little region allocated to it for all of its variables. So all the variables that we define in main, let's say I make an int a equals 5. This variable a has a fixed size known at compile time. So the compiler knows, okay, I need to make space in my main stack frame to store a. This will be the size of an integer, and I can now store in that memory section values for 5. And if I make an array, let's say int b, array of length 5, this will allocate enough space for 5 elements. So if that was one element, then maybe I'm saying like 1, 2, 3. Okay, you know what? This just block here can be b. Let's say it has space for 5 integers. But we can't exactly make guarantees about whether or not it's contiguous. Exactly, there may be some padding spacing. That depends on the compiler and the specific system. But what we can say is it will fit in the stack frame, and it will be known at compile time and be constant. The ordering may also vary. It's a compiler choice, implementation detail. But these are all contiguous. And then if I have another function that gets called, let's say I call func with some arguments. Func gets put on the stack right below. If I were to rotate my screen around, it would be like a stack of books growing upwards. If here the stack is growing downwards. But now I have memory allocated to function 2, or whatever function I've called here. So if I did try to resize this B array, it'd be intersecting with that section allocated to func. So I cannot resize things because the compiler has to know how big things are at compile time. And if you try to go out of bounds and you try to access B of 10, now you're going to be accessing out of your memory section. So being careful with bounds is really important in C. They don't necessarily get enforced. Sometimes they do. If you want to have dynamically sized things, this is where the heap comes into play. Note, the stack implements the stack abstract data type. The heap is not a heap data structure. It's just called the heap, different concept, different thing. Do not get them confused. The idea behind the heap is you basically have a little person counting, or I've been saying person, anthropomorphizing, but it keeps track of every allocation and how big the allocation is. So imagine it sort of like a parking building. Every person has their allocated parking space. Even if they're using it or not using it, no one else is allowed to park there. If you get allocated space in the heap, it's yours until you give it back. That's an important note. So how do I use the heap? In my stack, I can store something fixed size. For example, a pointer is a fixed size and can be known at compile time. All pointers will be the same size. So in my stack section, instead of storing, for example, a variable like a, I might store a pointer to an integer. So it would be an int star a. And notably, this syntax of int star a can be a bit confusing sometimes. So it can also help to think about, you can put the star on the other side, int star a. That can make it a bit more clear that a is storing a pointer to an integer, an int star. The convention for syntax in this subject puts it on the right. You can also put it with space on both sides. But specifically, a is an int star. So if you ask what is the value of a, it's an int star. If you ask what is the value of star a, if you remove one star from the int here, we see, okay, star of a is an integer. So star of a goes to the location specified and stored in a and gives you the value, an integer. As a brief note, ampersand of a gives you the address of a, which is a pointer to an int star. So this would be of type int star star, where this is a pointer to an int star. So it can get pretty confusing. I'll leave that for a moment. But practically, to get space on the heap, we have to use the memory functions that C gives us. So one of those is called malloc, where the M stands for memory and alloc stands for allocation. And this will give you a pointer to a section in the heap of a given size. So if I had malloc of 10, this would give me space for 10 bytes in the heap, and it will give me a pointer to the start. So this is what it returns. Notably, normally you would not do this. This is a bad idea. You need to make sure the thing you're asking for, and the amount of space you're asking for, corresponds to a given object. So usually, to make it safe, we use what's called the size of operator. So I have, for example, size of int. And the reason you should use size of is because the size of types will vary by a given system. On one system, it might be 4 bytes, on another, it might be 10. So in order to make it work on any system and not change between compilers or different versions, we use size of. So at compile time, the compiler determines how big is this type, and then it replaces all these occurrences with the right number. So for example, size of int on my computer would be 8. On your computer, it might be different. If it's really old, or if it's really new, maybe in the future it'll be 16. We don't know. And it gives us a pointer. But malloc doesn't have any information about what type you're dealing with. So what we do to make things generic with pointers is it gives us a void star pointer. So void star is just a generic pointer, which we can do because every pointer on a given system is the same size. So in order to allocate something, for example, as an integer, I might do int star a equals. And then I'm going to have my malloc call. And if I want one integer, I'm going to put size of int. And then technically speaking, doing anything with this is not required. If I don't have anything in there, this is going to do an implicit cast and convert the void star into an int star. Notably, the recommendation from this subject is that you always cast your types. So if I put a int star here, now the void star becomes an int star. And what this protects against is sort of you, the programmer, forgetting to change things. Because imagine if you wrote this on another line without the int star part, and you did a equals malloc size of char instead of int, you're going to have a memory bug. But if you always explicitly cast it, then if these don't match, you'll get a compile warning, which is safer. So it's sort of there as a documentation feature. But to make it even safer, instead of using explicit types, star of a is also an int. So I could also write star of a inside here. And now this will just update with the type that you pick on the left. So you can't break it that way. And then technically, you might want to not add this because then you only have to change the type in one place. The convention given in the subject textbook and such does keep it there, because in this specific case, if you do that, the only way this will change is if you change the type. Now you have to change it in 2 places. It will not compile if you don't change it. So it doesn't really add anything except one extra step of double checking. And double checking is good. We want to have the ability to check things, because memory bugs are very common in C. So various choices, but sort of that's the best idea, is just pick the name, star of the name gives you the type. And that will give you enough space, and it's going to give you a pointer. So in this case, for example, it's going to give me space to store one integer. And if this is at location, let's say 0x5ff, just the hexadecimal big number, this could be like 57 Swanson Street if I was, using street addresses from outside Unimel. Then inside my main function, if I had int a equals blah, blah, blah from before, a's value would be a memory pointer or address location, which is just a number, but this could be like 57 Swanson Street or something along those lines. It's a location, except now it's just a number corresponding to where we are in the memory, because the memory is just this big, effectively long array with indexes from 0 up to a very big number. So if we know the index, that tells us the location. And sort of that is how we have our heap memory allocated. We have to be careful though, because if I do a malloc call, I always have to free the memory. So if I did malloc here, sorry for the messy writing, hopefully it's readable, then at some point I should free the space allocated to me. If your program exits and returns, any memory you've mallocked will be given back to the operating system. If your program is a web server that runs continuously without stopping for 1 year straight, and you keep forgetting to free the memory, over time, you're going to be using up more and more space. And over time, you're going to run out of space eventually. So this is called a memory leak. The idea is if you remove all pointer references to your heap allocated memory, you have no way to free it anymore. And if you keep doing that, you're going to use up all the space. Even if it's unused, now you can't allocate more things. So if you look at this room, if 10 of the seats were reserved for people who are not here, and we didn't let anyone sit in them, and there's some people waiting outside who want to sit down, if the seats are reserved, even if no one's using them, now there's no space. But if you always give the memory back, all the free seats in the room can now be filled by whoever wants them. So that's the idea behind a memory leak. So if you can write like a few lines of C code where you malloc space in a for loop without freeing it, you will crash your computer. So that's how easy it is to be pretty uncareful with memory allocation. Okay. So just because usually there's a bit of confusion with pointers, as a bit of an example. So I have house number 1, which stores the number 5. And this is at 1 Swanson Street. Swanson Street. And maybe I have a driver's license telling me 1 Swanson Street. And it's telling me, there's a number 5 at that location. So if I have this driver's license, I could have 100 copies of it. If anyone with that driver's license, or I guess party invite or something, goes inside the house 5, they'll see the number 5. Anyone who has that location can go inside the house and change the number. What I could also do is tell you where this is. So let's say I left my invite in my house at 2 Swanson Street. Then I could have another piece of paper, telling you to go to 2 Swanson Street to find a pointer to the actual location of the number. So this is our int star. It's another thing. I could make as many copies of it as I want. I go inside 2 Swanson Street. I find the pointer to the int, the final location I have to go to, and I follow that over, and now I can modify the value. But notably, I can have as many copies of these as I want. I could have another one over here saying 1 Swanson Street, which is at a different location. And they can all point to the same thing, which is why I'm able to make copies of my pointers throughout my program and not have issues, because I'm always going to be modifying that one single source of truth. But if you want to modify this as a value, I then need a pointer to this. So if this is at a different location, then I know where the location is to go change this value, but this also knows where this value is. So you can sort of follow along with as many layers. You can have an int star, and that's having a pointer to an int star. And then sort of so on and so forth. The idea is always, I'm pointing to the location of the value I want to change. And if you have enough stars, you can keep following along and dereferencing until you get to a physical non-pointer value, which exists. And addresses sort of follow along from our street addresses, but it can be pretty confusing. But sort of, if you track through it, it ends up being sort of two operations you have to keep track of. Okay. Any specific topics in FOA you want me to discuss? No? Okay. Okay, I guess as a bonus thing, time complexity, bit of extra details on how to determine time complexity of loops. The biggest mistake that I see in the subject personally is thinking that nested loops means you can multiply the time complexities. That only holds if they are independent from each other. So if I have one loop, which is for int I equals 0, I is less than some input n, and then do I plus plus. And then I have another loop like for int j equals 0, j is less than n, and j plus plus. Then because these do not depend on each other, they only depend on the input, the inner loop will always do n iterations. The outer loop will always do n iterations. So then I'm doing n times n things, n times n things, n times n things. One time n things, and overall n times. And so my total iteration looks like n plus n plus n plus n times. So I get n squared. If you draw this as a picture, in this case, it looks like a square, and I have on this sort of axis, I'm doing pairings of I and j. So if this is my I, j, if j goes from 0, 1, 2, up until n, I goes from 0, 1, up until n, then I have every single one of these boxes filled in with a pairing. If you make some changes, let's say this now goes to n on 2, then now I'm halving one dimension. But still, I have a nice complete square or rectangle. And so I can multiply the complexities. It gets a bit interesting when you consider, okay, what if they depend on each other? That's where you have to be very careful. So if I have j's less than I, now I have to be careful because the inner loop in the first case, I starts at 0. Is j less than 0? No, I don't do anything. So then I'm doing 0 things. The next iteration, I is 1. So I do 1 iteration of the for loop. The next time I'm doing 2 iterations, then 3 iterations, then 4 iterations, until I get to n. This is now dependent. The inner loop depends on the outer loop. It's not constant every time. So if you looked at our pairing diagram, for the I and j 0 value, we don't do any iterations. But from this point onwards, if we look at the picture, we are doing work. And if we look at this sort of as a square, we have perfectly bisected it in half. We have the area of a triangle, in essence, which is half of n squared. And if we also consider this in terms of 1 plus 2 plus blah, 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 plus n, that also is approximately half of n squared. So that sort of approximation out follows. You can do it either based on that formula being n squared, n times n plus 1 over 2, or looking at the triangle shape. And that area is half. So that's still big O of n squared. But there are cases where this is not true. For example, this can be some other arbitrary function. It could be like logarithmic or exponential growth. And then you have to be very careful about the bounds of iteration. So as an example, if I want this to be logarithmic, I might start with making a couple of changes. So I'm going to make this a less than or equal to. This can be starting at 1. And instead of increasing by 1 every time, I'm going to double it. So star equals 2. So now I'm doubling every time in a fixed width of n. and doubling every time to be less than n will take me, to be greater than n will take log of n steps. So this outer loop does log of n work, and the inner loop is doing I iterations. So I'm doing log of n, or log of 1 plus log of 2 plus log of 4 plus so on, iterations. Now, in this case, we have to do a bit of analysis and see how many iterations will this take. And to make the analysis a bit easier, it's nicer if we don't have values starting from 0. So I'm making this less than or equal to, and I start this from 1. That just makes it easier for me to analyze because starting from 1 is a nice number. So now that I have that, let's compute the pairing. So I have my first value of I. So I is 1. And then we have the values of j, which are less than or equal to I. So I consider the value of 1. And then I have I is 2, and I'm doing 1 and then 2 for j. And then if I have 4, I have 1, 2, 3, 4. And I have 8 because I'm doubling. I have 1, 2, 3, 4 up until 8. And then if I have n things, I'm doing 1, 2 up until n. And then once I get larger than n, I'm stopping. So then now we have to consider, okay, how many iterations does this go with proportionally as a function? Because that's the goal, right? And notably, this is not linear. This is sort of growing according to some function. If you reframe things on the left, which is what I usually like to do, sort of you can consider this as we have 1 box and then 2 boxes, and then 4 boxes, and then sort of so on and so forth. This looks like an exponential function because it is. And the question then becomes, okay, how wide is this part? Well, if this part here is this axis, and we know there is going to be log of n things here, because that's how I iterates over, we are growing exponentially with our log of n here. Now, I will save you the discrete math part in too much detail, but in essence, we are asking sort of what is the area of these boxes add up to? Same as before. Now you could do this doing discrete sum, so we can consider the sum. Okay, I'm going from I equals 1 up until log of n, and every single time I am doing I work. That's effectively what we're trying to do. And you can show that this sum equals something. So this sum gives us a value. Now, it's a bit annoying to work out, but you can sort of follow from like the geometric series rules. What I tend to like to do for this, which you don't have to think about too hard, is you can also approximate this with an integral. I'll say the details beyond its monotonic increasing sequence. If you want proof or something, let me know. I can chat about it. But once you have the formula, if you find the expression this equals to in closed form, that will tell you how it grows. And that may or may not be equal to the value that you had to start with. Oh, actually, notably, this is not I made a mistake. This doubles every time. So this is 2 to the I. Sorry. Minor mistake, but logic applies. To save you the details, this ends up being approximately 2 to the log, if this is base 2 of n, which is approximately n, and if this is big O, sort of they end up being equal to big O of n. So unless I made a mistake, I haven't fact-checked this or planned talking about it, so bear with me. But you know, that is very distinctly not n log n. That's O of n. That is also the logic behind, for example, how something like building a heap takes O of n time instead of n log n time. The exact details are slightly different. The top outer loop iterates over n over 2 things, and the inner loop is dependent on that outer loop. How many iterations you do in sift down depends on that outer loop, which is how you can get something that's O of n when you're doing something that's quote unquote log of n operations n over 2 times, because it's actually dependent on the outer loop value. So you have to be very careful in this dependent loop case. If they're independent, you're having happy days, just multiply them. But otherwise, be very careful. There is some details on the tutorial sheet, I forgot which number it is, about dependent loops with a bit of worked examples for this, which I'll not skim through. I did write those, so You can view them on Ed if you did. Okay, I think that covers things, and we're also a bit over time, so.
Well, first of all, I'd like to thank you, all three of you for attending this workshop. We really appreciate it. Thank you for trying to organize these and get like tutors like, Brian and in this case, Casey, to help